Hello everyone. Today we're going to look at a number system that may not be so familiar to some of us. And for that reason, I thought I would make this video. So let's get into it. We have 10 different symbols, 0 through 9. In this system, the place value of each digit increases by 10 as we move from right to left. How could we possibly count anything using just those two symbols? Let's take a look. For example, in the number 3241, the digit 3 is in the thousands place. We start out with 0 matches and place a 0 down. Now we use one match and there's not really anywhere to put it, so we place it next to the 0, giving us 01. Because the value of the places in this system are powers of 2. ULL. See what I mean in a moment? Again, we're showing that the unit's position is now worth 2. We place the new match in the next position, giving us 1100. This time the 2 position is now worth from. We place the new match in the next position, giving us 10,001. At this point, we've used up all of our matches and we can't really do anything with them. The powers of 2 are 1, 2, 4, 8, 16, 32, 64 and 128 in the positions from right to left. By lighting this one, we're showing that this position is now worth to. We then place the new match in the next position over, giving us 1001. We light the first match again, showing that the 4 position is now worth 8. We place the next match in the next position, giving us 1,010,000. And not only that, but each of these binary numbers are unique to its corresponding natural number. We have the number 7. Converting this to binary, we end up with 111. Notice that if we were to change any of these digits, we would end up with a different number. For example, if we changed the 1 in the unit's position to a 0, we would end up with the number 6. If we changed the 1 in the 2's position to a 0, we would end up with the number 5. And if we changed the 1 in the 4's position to a 0, we would end up with the number 3. So we will light both of them to show that they are used up. Starting with 47, we divide by 2 to get a quotient of 23 and a remainder of 1. Then we divide 23 by 2 to get a quotient of 11 and a remainder of 1. It's called the place value method. All you have to do is multiply each digit by its corresponding place value, and then add them all together. We divide 11 by 2 to get a quotient of 5 and a remainder of 1. First, we multiply each digit by its corresponding place value. 1 times 1, 0 times 2, 1 times 4, 1 times 8, 0 times 16, and 1 times 32. Then we add them all together, which gives us a sum of 47. Then we divide 5 by 2 to get a quotient of 2, and a remainder of 1. And finally, 2 by 2, which gives us a quotient of 1 and a remainder of 0. Reading the remainders from bottom to top, we end up with the binary equivalent of 47, which is 101,101. Every time you run out of matches and need to add another one, you light the leftmost match that hasn't been lit yet. This means that the binary system is unique in the sense that each number can only be represented in one way. This is also true of the decimal system, but it's not true of other number systems, showing that the place value of that position is now double the number of matches it was before. If you did, please hit the like button and consider subscribing. Thanks for watching. You then place the new match in the next position to the right. If there is no lit match, we place a 0. Moving from right to left, we end up with the following numbers. We start out with the number 13, then we divide by 2. The quotient is 6 and the remainder is 1. Starting with 29, we divide by 2 to get a quotient of 14 and a remainder of 1. Then we divide 14 by 2 to get a quotient of 7 and a remainder of 0. We divide 7 by 2 to get a quotient of 3 and a remainder of 1. And finally, 3 by 2, which gives us a quotient of 1 and a remainder of 1. Reading the remainders from bottom to top, we end up with the binary equivalent of 29, which is 11,101. Then we divide the quotient 6 by 2, which gives us a quotient of 3 and a remainder of 0. We divide the new quotient 3 by 2, which gives us a quotient of 1 and a remainder of 1. Finally, we divide the last quotient 1 by 2, which gives us a quotient of 0 and a remainder of 1. Reading the remainders from bottom to top, we end up with the binary equivalent of 13, which is 1101. We grab another match and light the first one we grabbed, showing that the 2 position is now worth from. We place the next match in the next position, giving us 100,010. This number system is called the binary number system. And yes, It really is as simple as math. Let me explain. We use the decimal or base 10 numbering system every day. But what if we used a different number system? What if we only had two different symbols, like on an electrical switch, where 0 represents off and 1 represents on? Here we have an unlimited supply of matches, and we want to keep track of how many we have used. It turns out that each arrangement of lit and unlit matches represents a unique binary number. Let's take a look. Now we go to grab another match and light it. And since we don't have any place to put it, we place it next to the other two. This gives us 101. At this point, we run out of matches again. So we light them all up. Now we grab another match and repeat the process. We end up with 110. Again, we run out of matches and we light them all up. Now we grab another match and this time we re-go in to light the first one that we grabbed. The one that was in the units position. If you're wondering why we're lighting the first match, we grab another match and place it in the next position, giving us 1010. Then we grab another match and light the first one we grabbed. Now we grab another match and place it in the next position, giving us 1110. We run out of matches again and light them all up. We grab another match and light the first one we grabbed. Now you should be starting to see a pattern here. Now, let's grab another match and place it in the next position, giving us 10010. Now we grab another match and place it in the next position, giving us 100,011. And you can continue this process to count as high as you want. So, as you can see, using this method with matches, we can easily keep track of how many matches we've used without having to worry about grouping or anything else. But how can we convert this to something more useful? Starting from the right side, if there is a lit match, we place a 1 in that place value. So as you can see, we can represent all of the natural numbers using the binary system. Let's take a closer look at this. The same thing applies to any other binary number. If we change any of the digits, we end up with a different binary number. For example, the number 12 can be represented in two different ways in base 8 or octal. But as you can see, this is not the case in binary. Now that we understand how the binary number system works, let's look at a few more examples. First, let's convert the decimal number 13 to binary. Let's convert the decimal number 29 to binary. Let's convert the decimal number 47 to binary. And remember, each of these binary numbers are unique to their corresponding natural number. There are many different ways to convert from binary to decimal, but this method is one of the easiest. For example, let's convert the binary number 101,101 to decimal. I hope you enjoyed this video.